Hello, everyone. In this video, we are going to discuss extreme values and saddle points of functions of several variables. In a previous video, we discussed relative maximum and relative minimum. A relative extremum sits at a stationary critical point where the first-order partial derivatives of the function are both zero, which implies that the gradient of the function is the zero vector. Saddle point. It is a point in the surface that is a maximum, a minimum, or neither, depending on direction. But just like a maximum or a minimum, it is located at a stationary critical point, where the first-order partial derivatives of the function are both zero. Saddle surfaces. These are smooth surfaces in 3D space with one or more saddle points. Saddle point is located at a critical point, where the first-order partial derivatives of the function are both zero. The first surface is a hyperbolic paraboloid with the following equation. This is the value of the function at the critical point. So the saddle point has the following coordinates. The saddle point is a relative minimum when the surface is traversed in the x direction. But the saddle point is a relative maximum when the surface is traversed in the y direction. The second surface is a monkey saddle with the following equation. This is the value of the function at the critical point. So the saddle point has the following coordinates. The saddle point is not a relative extremum when the surface is traversed in this direction. And the saddle point is also not relative extremum when the surface is traversed in this direction. Absolute maximum and absolute minimum. An absolute extremum is the extreme value of a function on the domain of the function, and not just on a neighborhood or near a critical point. An absolute maximum is the highest value of a function for all points in the domain. Meanwhile, an absolute minimum is the lowest value of a function for all points in the domain. An absolute extremum can exist at a critical point or at a boundary point, in contrast to a relative extremum which can only exist at a stationary critical point. Nevertheless, a relative extremum can be an absolute extremum if it is not only an extremum on a neighborhood but also on the entire domain. An absolute extremum is located at a point where the function is continuous, which may be differentiable or not. Let us show more illustrations involving absolute extrema. Consider these graphs of a function of two variables, which are defined on the entire real plane. In the first graph, this is the critical point of the function where the partial derivatives of the function are zero. So the function is differentiable at this point, and the surface is smooth. The lowest point in the surface on the entire domain of the function is the absolute minimum. And this is the corresponding value of the function. However, the function has no absolute maximum because the function increases indefinitely on the given domain. In the second graph, these are critical points of the function where the partial derivatives of the function do not exist. Hence, the function is not differentiable at these points. And the surface has corners. The highest points in the surface on the entire domain of the function are the absolute maximum. And this is the corresponding value of the function. However, the function has no absolute minimum because the function decreases indefinitely on the given domain. Extreme value theorem. It says that a continuous function has both an absolute maximum and an absolute minimum if the domain is closed and bounded. Please consider the following graphs of functions of two variables. And the highlighted part of the xy plane refers to the domain of the function. In the first graph, the function has the absolute maximum and the absolute minimum, and each extremum is achieved at a boundary point of the domain. In the second graph, the function has the absolute maximum at an interior point of the domain, or to be more specific, at a critical point of the function. And the absolute minimum is achieved at the boundary points of the domain of the function. What if the domain is not closed and bounded? Please consider the following graph of a function of two variables. It is the same as the first function in the previous page. But in this case, the domain is the natural domain of the function, and in this example, it is the set of all ordered pairs of real numbers. The domain is open and unbounded. So the function has the absolute maximum achieved at a stationary critical point. While it has no absolute minimum, even if it appears to be approaching the minimum value of the function in some or all directions. Next, consider the following graph of a function of two variables. It is the same as the second function in the previous page. But in this case, the domain is the set of all ordered pairs that satisfies a couple of inequalities. This translates to a part of the boundary being excluded from the domain. The domain is not closed but bounded. So the function has no absolute maximum, even if it appears to have achieved the maximum at a boundary point, which is not included in the domain of the function. Meanwhile, the function achieves the absolute minimum at a boundary point of the domain. Therefore, the extreme value theorem is invalid when the domain is not closed and bounded. Now let us enumerate a strategy in finding absolute extrema on a closed and bounded domain. First, determine the critical points in the domain of the function. Do this by setting the first-order partial derivatives of the function to 0. And then solving the two equations simultaneously for the critical points, which are pairs of values of x and y in the domain that force these partial derivatives to be equal to 0. Please consider the following graphs of functions of two variables as an illustration, as well as the domain of the function over which extrema are required to be located. A function may have one or many critical points in the interior of the domain, as shown in the first figure. A function may not have a critical point in the interior of the domain, as illustrated in the second figure. Note that a critical point may appear at a boundary of the domain, which now makes it a boundary point. And then compute the value of the function at the critical points. Second, identify the boundary points of the domain. Group boundary points such that each point in a group can be represented by a more general point. And compute possible extreme values of the function in these groups of boundary points. There are boundary points whose values are easily computed by direct substitution. And there are boundary points whose extreme values need a couple more steps to find. In the first graph, we know that cosine achieves a maximum at 0. So this is the extreme value on this side of the domain. In the second graph, we can find the maximum and minimum of each single variable equation using techniques studied in Calculus 1. Or use our knowledge about sphere and deduce the extreme values on the given domain. Now we have the values of the function at the critical points and the boundary points, which are the candidate locations of extreme values. Third, the absolute maximum is the highest among the computed values. While the absolute minimum is the lowest among the computed values. Let us revisit two illustrations we had earlier, but this time, the domain of each function is closed and bounded. In the first graph, aside from having an absolute minimum, the function now has an absolute maximum, which appears on these points in the domain. And this is the absolute maximum value. In the second graph, aside from having an absolute maximum, the function now has an absolute minimum, which appears on these points on the boundary of the domain. And this is the absolute minimum value. Please watch the previous video about critical points, boundary points, and relative extrema. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.